Hi guys, welcome to your Chapter 6 Part 1 video. This video will be, well, I guess there's no point in telling you because you can look at the YouTube video length. I don't think this will be very short. This is the biggest idea. It's sort of a culmination of ideas that we've looked at from Chapters 3, 4 and 5. 4 and 5 specifically. And what we're going to talk about today, I know I probably said this a few times already, but it is central to the rest of what we're doing in statistics. Once we have worked with the standard deviation as a ruler, we call the standard deviation as a ruler is a z-score. Once we've worked with that a little bit, we'll have more flexibility in topics that we can discuss, things that we can compare and contrast, etc., etc. All right, so let's check out what we got here. We've got 3 competitors in a 3-event competition, so it's like some sort of funky triathlon. We wanted to determine whose overall performance was best. So each of competitors A, B, and C did the 100-meter dash, the shot put, and the long jump. We've got their times or their distances, and we've got the mean as well and the standard deviation for all the competitors of the 100-meter dash, all competitors of the shot put, and all competitors of the long jump. It's really hard to, without using a z-score, talk about how competitors A, B, and C are better or worse than each other. So we're going to build up to what the z-score is. We're going to get a lot of practice with it in the notes because it is new. It will feel a little different, but once we're accustomed to it, we'll find that it has a ton of applications and we can use it all over the place, even outside of this class. Let's see, so currently we don't have adequate tools to determine winner for the competition. However, the use of standard deviation of a few new tools will allow us to determine the overall performance, or whose overall performance was best by the end of the day, by the end of the notes. We're going to look at that. Alright, so we're coming back to the question of slide 1. That will return once we've got our z-score. Here, we're going to check out a, what? I thought I already changed that. Change the color scheme. Keep. Alright, here we've got a data table, and this data is from John Beal, who, this is not made up. He recorded the speeds of cars driving past his house 100 times, where he knew that the speed limit was 20 miles an hour. So low speed limit. I guess this guy was perturbed, and you've got the data listed. I plugged this into Excel, put it in ascending order from top left to bottom right, and yeah, so this is the data that we're going to look at. First application of this data, you've got 2 exciting histograms of wow, 1 and 2. They are a little bit different. On the left, you've got the 100 data values, so 100 car speeds that were passing by John Beal's house. I would say that this distribution is unimodal, with a mode at about, oh, what a weird way to organize the bins. That's not a very good, made this last year. As I hope you guys are noticing, these numbers are not referring to the bin cutoff points, dividers, as they should be. For some reason the numbers are just talking about the bins themselves, probably the center of that bin. So anywho, histograms are a little off. The data's okay though. So in the first case we've got a mode at about 25, second case mode at about 5. The way that we have gone from the second distribution to the first is by subtracting 20 miles an hour from every data value. So the shape, as you can tell, comes out to be about the same from histogram on the left to histogram on the right. We do have some negative speeds on the right distribution if you subtract 20 from every data value. But the real crux of this slide is, how do the statistics that we have used so far to measure spread and center change, or how have they not changed? Well, I think you can see pretty clearly that the mean on the left, even if, well, we know if the median, where the center of the data is according to cutting the area into equal halves, is at 25. Because the data is a little bit right skewed, the mean might be just barely to the right of the median. Median dashed mean, solid. Okay, so there's the median and mean for the first data set, for the first distribution. On the right, even though it's in the same shape, you've got median maybe right about here, mean right about here. Because all of the data values are lower on the x-axis, obviously the mean has been changed in the process. IQR, however, let's go to a different color here to represent the IQR. The IQR should not be changed. If we've got the median being the dashed lines in each of these two distributions, and we know the quartile 1 is basically the median for the left half of the data, quartile 1 could be like right in here. There's Q1. And we know that to find the interquartile range, it's the difference between Q1 and Q3. Q3 may be like right in here. Let's draw that from the top. Q3. So your IQR here is actually going to be the same as it would be over here. Q1 and Q3 are relatively speaking in the same positions in the second histogram. So even though we shifted all the data down 20 units, the IQR has not changed. Okay. How about quartile 1? Well, yeah, obviously we just saw that changed. Even though, again, quartile 1, that leftmost black dotted line, is in the same spot in the distribution, it is further down the car speeds axis on the right distribution. So quartile 1 has changed. Has the range changed? No, because the difference still between lowest and highest data values for both distributions is the same. So the range has not changed. Median, we note, has changed. And the standard deviation, how far everything is from the center, as measured by the mean, the solid red line that we have in each distribution, well, that shouldn't be changed either. Even though everything's shifted, for instance, the data value that's like right at 35.8 over here is just as far from the mean in the left distribution as it is here in the right. Even though that's marked as more, it should be the same distance. So standard deviation has not changed in the process of shifting all the data values down 20 miles an hour. So this is a universal truth. If we add or subtract a constant to or from our data, statistics of position, the mean, the median, the quartiles, the min, and the max are added or subtracted by the same constant. Statistics of spread are unaffected by a shift in the data. I think we need to write out an example of this to clarify further. So let's say that we've got a distribution for which the mean is 20. If I add 10 to all x sub i's. What is an x sub I? An x sub I is some data value in the data set. X sub 1 would be the first, x sub 50 would be the 50th, etc., etc. Then x bar, the mean changes similarly. It changes in suit. If we have a mean of 20 and we subtract, not 20, subtract 10 to all x sub i's, then x bar again changes in suit. It would fall by 10. So because x bar is a measure of spread, and we said the universal truth was that statistics of position, when we shift in this way, are all added or subtracted by the same constant. Likewise, if you had quartile 1 at 20 and added 10 to all your data values, quartile 1 would jump up to 30, just like x bar did in this particular case. So examples that would be affected this way: quartile 1, the median, quartile 3, etc., etc. Anything that measures position for the distribution. Okay, on the other hand, let's say that S, standing for sample standard deviation, is 5, and I continue to, just like I did in the very first row, add 10 to, why do I keep making that an A, to all x sub i's. Then S would be unchanged. The distance that everything is from the mean as a measure of center would not be affected. And similarly, if your sample standard deviation is 5 and you subtract 10 to all x sub i's, then your sample standard deviation again would not change. Because sample standard deviation is a measure of spread, we know that also a measure of spread includes range in the IQR, how far the data values are from each other. They too would be unaffected if you added or subtracted all the data values. So IQR and range are also in that same boat of being unaffected by shifting the data. Okay, that's the first piece to build up towards the z-score. Shifting changes measures of position, but not measures of spread. On the other hand, if we got two distributions here, the one on the left, are the titles appropriate? Nah, probably not. But first year that this was designed, it was made pretty late at night, and that's what you get. So tough. We got Excel is beastly on the left, and this is the same distribution of 100 data values that John Beal got, just in a window it's farther across, because to get from the distribution to the left onto the right, we multiplied every one of the drive speeds by 2. Notice lowest data value for the distribution on the left is like at around 16.5, 16.6. Right over in here, there are a couple of them in that first bin. We multiplied all the data values by 2, and now instead of 16.5, you're looking at about 33 for the lowest data value. Similarly, the high data values were affected. We went from 35-ish to about 70. So everything was not shifted. We call this scaling, when you multiply all the data values or divide all the data values by the same number. Right, so which of the following statistics would be influenced by scaling the data in this way? I would like to avoid cutting things like I did here to show you the IQR, median, mean, etc., etc. Just in the interest of time, let's see if we can see which ones would change. Would the mean change? Absolutely. Mean was low over here, wherever it might be, let's say in there. Mean right over there, so absolutely the mean changes. Would the IQR change? Yes, the IQR as a measure of spread would also change. Notice that the distribution on the right is more spread out. It should be about twice as spread out as the distribution on the left. Is it that? No, maybe not. Maybe the bins are off by just a little bit, but it should be about twice as spread out. So the IQR has been changed. Has quartile 1 changed? That's again the position at which 25% of the data is less than that point. Yeah, because we bumped everything up on the x-axis, or at least on the car speeds axis in this case. So quartile 1 has changed. Has the range changed? Yes, because, like we just said, this width is approximately half of this width over here. So the range has changed. Has the median changed? Yes. Similarly, like the median has changed. We bump everything up. Has the standard deviation changed? Yes, again, because distribution on the right, everything's farther apart. By bumping everything up by multiplying by 2, that makes your gaps twice as big. So the standard deviation has changed as well. Okay, cool. So, universal truth. Scaling the data by multiplying or dividing, as was done to produce the second histogram, affects both measures of position and measures of spread by the same factor. Okay, again, like I did last slide, I'm going to write this out in a slightly formalized way so you can have this in your notes, and I think it'll help when we hit the z-score piece. Alright, so we talked about all of those 6 things, those 6 statistics up here being changed. If we've got, for instance, like we did last slide, x bar equaling 20, and we multiply all the data values by 10, then x bar should go up to 200. It just scales according to that scale factor of 10. X bar equaling 20. If we were to divide through by 10 to all the data values, then x bar would also just be equal to 2. It would change as you would expect it to. Remember, x bar is a measure of position of the data because it's a measure of the center of the data. So also affected in this way, you would have quartile 1, median, Q3, etc., etc. Anything else measuring position. Okay, so if we have, for instance, moving forward, if we have a sample standard deviation of 5 and we multiply all data values by 10 to all x sub i's, then sample standard deviation would also adjust accordingly. It would go up by a factor of 10, so it would go up to 50. Just like we saw up here. We saw when we multiplied everything by 2, the width of the distribution basically doubled. It may not look like exactly that, but it's more or less what should be going on there. Any error that you see in the widths would be just me not having set these widths here of the pictures correctly. If those widths are not the same, then that would be my fault, and I wouldn't have necessarily violated the area principle, but it makes for a tougher comparison visually. Alright, so S is equal to 5, multiply everything by 10, you get a sample standard deviation of 50. If you had a sample standard deviation of 5 and you were to divide through by 10 to all x sub i's, then your sample standard deviation would be equal to 0.5. Okay. These sample standard deviations being measures of spread, well, in that same boat would be your IQR, your range, and let's see, IQR, range, anything else that we would measure spread with. I think that's all. Let's see, IQR, range, sample standard deviation. Yeah, that's the only formal quantitative measures of spread we have at this point. Okay, so there you go. If you shift the data, measures of position are affected, but not measures of spread. If you scale the data, both are affected. All right, so now we get to the heart of the slide, or the heart of the notes rather. To compare sets of data that would normally not be compared, we're going to use both shifting and scaling to produce a new statistic called a z-score. To compute a z-score from a data value, and yes, they are found for any data value, we use it is an incredibly useful equation, this z equals x minus x bar over s, where x is the data value that we care to find a z-score for, x bar is the mean for the data as we've used it in the past, s is the standard deviation of our data, I should really say the sample standard deviation as we've used it so far. Okay, so let's go ahead and pause here to compute the 9 z-scores for the data table from the first slide dealing with the triathletes. Okay, so we're looking at, if you're going through with your notes with this, we're going to find z-scores for these 9 times or distances for these 3 competitors here. And the z-score equation, we're going to use this z-score equation 9 times, and I'm going to speed it up because you don't want to see that calculated 9 times, is using the sample mean and the sample standard deviation listed in that first slide. For like long jump distance, we're going to use this x bar and this s whenever we're trying to find a z-score for a long jump. Okay, enough talk, let's get to it. So for competitor A, I'm going to go from my notes here, I'm not going to go back and forth. For competitor A, we've got, let's find the z-score for their dash time, their 100 meter dash time. That's equal to, well, x is the data value for which we care to find a z-score. That is equal to 10.1 minus x bar, so the mean time of all the 100 meter dashes is 10 seconds, divide through by the standard deviation of those dash times, 0.2, again coming from the first slide, and that gives you a 0.5. Find the shot put distance as a z-score instead of the 66 feet that you saw. So we're taking 66 now as the data value for competitor A we care about, subtracting off the mean of all shot put distances, which is 60, and we're dividing through by the sample standard deviation was 3 feet, so you get 2 standard deviations. Okay. Now we are going to look at last piece here, the long jump distance for competitor A. Well, she or he, I think Tanya, Lexi, and I can't remember, so she probably, 26 minus, that's her long jump distance, minus the 26 feet is the mean. divide through by 0.5 for the sample standard deviation. It was a 6-inch standard deviation. Convert that to feet so the units are the same. There's your 0.5. That's equal to 0. Okay, so we've got the Lexi. If Lexi's competitor A was half of a standard deviation above the mean of all competitors in this weird sort of triathlon, in the dash, competitor A was 2 standard deviations above the mean in the shot put throw distance, and was right at the mean in the long jump distance. All right, competitor B, let's go to a different color for this. Her dash time as a z-score, she ran a 9.9. Subtract into the mean off of that. We've got 0.2 for the standard deviation there. That's negative 0.5. Okay, ask yourself real quick if competitor B's z-score here of negative 0.5, so negative 0.5 below the mean, is being below the mean of all the competitors a good thing or a bad thing in this case? Well, for this being a dash, a 100-meter dash, being below the competitors, 9.9 being below that 10, that should be a good thing. So don't assume automatically that negatives make you look bad or that positives make you look good. It's a matter of context. Okay, so shot put. How did competitor B perform there? Well, 60 feet for her distance minus the 60 feet for the mean, divide through by the standard deviation of 3, so right at average. Competitor B performed average in shot put. And then last piece, long jump distance, that's equal to, she had 27 feet minus the mean of 26 feet over 0.5 feet. Comes out to be 2. Is that a positive, or does that make her look good? Yeah, in this case a positive z-score does make her look good. She wants to perform for the long jump. The goal is a higher distance, so being at 27 versus the 26 average for all the competitors in this triathlon, that's a positive thing, so a z-score of 2 reflects well on her. Alright, last piece here, competitor C. We've got competitor Z has a dash time equal to 10.3 minus the mean of 10, divide through by the 0.2, which is the sample standard deviation. There's 1.5. So this last competitor actually did really poorly in the 100-meter dash. You would think maybe intuitively positive numbers would equate to success, but no, not with it being a dash. 10.3 is a slow time compared to the pack. On to the shot put next. We've got 63 minus 60 over 3. That's their shot put distance minus the mean of 60 over sample standard deviation of 3. That comes out to be 1. So they were 1 standard deviation beyond the pack in terms of shot put distance. That's positive that time because you want to throw further. And then long jump is equal to 27.25 minus 26, divide through by 0.5, and that comes out to be 2.5 for her last event in this triathlon. Okay, so you've got one competitor who was as good as the rest of the pack or better than the rest of the pack in these 3 events. Notice that competitor A here also had a positive z-score for their 100-meter dash. That would be a bad thing for them. That means they're slower than the rest of the pack there. Their shot put distance was good and they were average here. But competitor B had a negative z-score, was below the average for the 100-meter dash. That reflects well on them, was right at average in the shot put, and then performed significantly better than average in the long jump. Competitor D, below average, significantly below average in the disc, or in the dash rather. For shot put, did a little bit better, and then for the long jump did much better, 2.5 standard deviations beyond the mean. Okay, so we're going to come back to, I think I want to leave those numbers right there, and come back to interpreting it a little bit more here in just a second. There are a few reasons we use the z-score statistic to shift and scale our data. Because the z-score statistic subtracts the mean of the data from every data value, we're shifting the mean to 0. When you can make all of your data into z-scores, and if you do, because you're shifting, you're subtracting off the mean in this equation that's got the red circles around it right here, we are similarly changing the mean to 0. If you have the mean subtracted off, you get 0 back. Alright, and because the denominator is dividing through by s, the standard deviation, and we know that any measures of spread are affected by the constant we are multiplying or dividing by. If you have a sample standard deviation, you divide everything by the sample standard deviation, you're changing the sample standard deviation to 1. So z-scores are changing so that the mean looks like a 0 and the standard deviation looks like a 1. That allows us to take these disparate groups, these different competitors here, and compare them from their 100-meter dash in that first row to the shot put in the second row to their long jump in the third. Even those events are measured, and the competitions work very differently. By using these z-scores, you've got sort of a universal means of measuring from one distribution to the next. Okay, transforming the raw data into z-scores is called standardizing the data. We won't have to do that much. The larger or smaller a z-score is, the more interesting it becomes. A z-score of 2 or negative 0.2, or negative 2 rather, is 2 standard deviations away from the mean of the data. A z-score of 2.5 or negative 2.5 is 2.5 standard deviations away from the mean, etc. So quick summary of z-scores. Our shape is not changed when using a z-score, because all we're doing all we're doing is shifting the data by subtracting off x bar and scaling the data by dividing by the sample standard deviation. So shape is not affected. Think back to this right here. The shape was not changed when we shifted the data for those 100 drive times past John Beal's house. The shape of the data was not affected when we scaled the data by 2 for those 100 drive times. So shape's not affected, center is affected, but to make the mean 0, spread is affected to make the standard deviation 1. Okay, so let me write out formally real quick what I'm saying here. The big idea is, let's say you've got a set of data values for which the sample mean is 10, and we subtract 10 to or from all the data values. Well, suddenly the mean is at 0. Okay, we're talking more or less about the same type of data, but now we've got an easier mean to work with of 0. What's another comparison like that that I could analogize this to from another math course? Nothing's coming to mind. Sample standard deviation of 2. If we were to subtract 10 to all the x sub i's, because notice when you calculate a z-score, it starts with that subtraction, then you do the division. If I'm subtracting 10, does my sample standard deviation change? No, because that's a shift. So the sample standard deviation would still be 2, but then if I divide all the data values by 2, that will change my sample standard deviation to 1, because we know that scaling measures of spread affects them by that scaling constant. If you divide by 2, sample standard deviation is divided by 2. If you multiply by 2, it gets multiplied by 2, etc., etc. So the takeaway on this, basically, all you have to do to be able to compare and say how outstanding is a performance, an individual, a thing, you just have to compute their z-score and that will allow you to compare to other types of categories, other types of events in this case. So looking at who was probably best overall, we had competitor A doing poorly here, but because they had a z-score above average for that dash time, but then well in the next two categories. If we wanted to determine who was best, we would probably want to find someone who performed better than average in every category. In competitor B, we already talked about doing that. Their dash time was below the average. They had a negative z-score. Their shot put distance was perfectly average, and then they had a really good long jump, which was 2 standard deviations beyond the mean. So the 2 standard deviations better than how the average performer was. So that's good. Competitor B might be the all-around best choice for winner here. Competitor C, their dash was really abysmal. 1.5 standard deviations below, so that reflects on them negatively. Shot put was good at 1 standard deviations above. Long jump was really good at 2.5 standard deviations above. So if you're looking for the all-around best, you'd probably conclude B if you've got some sort of system like the Olympic Committee has set up to determine weightings. Maybe you wouldn't just look strictly at z-scores. But yeah, for the first time we've now got a tool to compare totally disparate events and make conclusions based upon those events with this z-score. Let's continue to practice. Okay, the college you'd like to, and I need to check time here. Oh gosh, okay. The college you'd like to apply to says that while there is no minimum score required on the SAT, middle 50% of their students have combined SAT scores between 1530 and 1850. You'd feel confident in your chances of acceptance if you knew your score was in the top 25%. You didn't take the SAT, you took the ACT. How high does your ACT score need to be to make it into the top quarter of equivalent SAT scores? So we want to know, you've taken the ACT. Let's see what you'd have to get on the SAT to be able to make top 25% for this, for all high school SAT takers. All right, so we know top 25% is at the 1850 mark for the SAT. Okay, so we're going to use a z-score here. We're going to find a z-score for that top 25%. I'm putting z-score sub 25% just as a way to keep track of what this z-score is referring to. That would be 1850, the z-score that we care about, because that's the mark at which you hit top 25%, minus the mean of all standard or of all SAT takers, 1500 divided through by the 250 standard deviation. And you get 1.4. That's the z-score for top 25%. So what do we do with that? Well, we want to know, just like we've done over here, we use z-scores to compare disparate events from dash to shot to long jump. Well, that z-score of 1.4, that 1.4 is also outstanding. That would also put you in the top 25% for ACT test takers as well. So we can say the following. We're going to use the z-score equation one more time. We used it once here, plugging in the x value we cared about, the mean and the sample standard deviation. Now we've got the z-score that we need. We want the x value corresponding to the ACT score that would hit top 25%. Subtract off the mean of all ACT takers, 20.8, divide through by the standard deviation of all ACT takers, 4.8, and that gives you, when you solve that for x, the x value corresponding to the ACT score we would want to hit top 25% would be 27.52. Okay, so we took something we knew would be exceptional for one numerical distribution, SAT scores, used that to calculate a z-score right here, and that z-score was allowed us to come up with what would be an exceptional z-score for a separate distribution of ACT scores. Kind of powerful. That is pretty powerful stuff. We're going from distribution to distribution. Okay, standardizing our data leads us to an important topic, that of modeling the data. The bell-shaped curve you probably heard of at some point is the normal model. Whenever the distribution of our data is unimodal and roughly symmetric, we can treat our data as normal. I think we should pause there. We're going to make this the first part of the video, and we'll continue these notes in class. I don't think that I should continue the video beyond this point.